Well, thanks for having me back. What'd you guys do last week? Launched 2 satellites into space, right? Was that last week or was that 2 weeks ago? 2 weeks ago, yeah. So, yeah, I'm not sure what time zone I'm in still. So, how exciting is it for us right now? We have 2+ of our own satellites in space, orbiting the Earth right now, every day. So the good news is we had Kentucky Sat 2 successfully launched. We had Eagle 1 successfully launched and Unisat 5 successfully launched. And now the work begins for the next phase of space mission operations, which is the ground operations. So I know some of you guys have volunteered your time and effort to be part of the ground ops team, and I would like to extend an invitation to everybody to become part of the ground ops team, learn how to use the VHF, UHF Earth stations, which is pretty easy, and then train on the big dish, which is a little bit more complicated, but we're willing to train you on both types of systems.
Well, and good on a resume.
And it looks good on a resume. I don't know if Professor Twiggs mentioned, but there was a company that called yesterday asking for graduates that have ground operations experience. So it's a whole different segment of astronautical engineering, which is mission ops and ground ops. And there are companies that do nothing else. You guys might have seen folks from the Universal Space Network floating around the building earlier in the fall. And they are a company that's actually owned now by the Swedish Space Corporation, and they manage a worldwide network of dishes to do ground operations. And they're always looking for employees. And they like us. They know what our students do. So it's a whole segment of the space operations business that you might not be familiar with. But so today, what I want to do is continue a little bit with the orbital mechanics lectures. We had a couple of days where we talked about orbital mechanics and satellite orbits and trying to understand orbits. But I sort of left off before I got to one critical piece of that, which was, the end, which related those orbital elements to the Keplerian elements that you need for ground operations. And so that's what I want to do today, is take about 20 minutes. I don't need the whole class. I'll turn you back over to Professor Twiggs, but I do want to make the connection between the orbital parameters and the Keplerian elements, and then how do you use those when you track satellites. So that's sort of the purpose of today's discussion. So just as a brief review, the KEPs, or the Keplerian elements, or the COEs, the common orbital elements, or sometimes you'll just see them as orbital elements, they're all the same thing. They tell you really about 2 things. You guys tell me, what do they tell you about? All of these different values tell you really only about 2 things about the satellite.
Where it is and where it's going.
Where it is and where it's going. That's a way to think about it. Where it is and where it's going. So really, another way to think about it is it really tells you about the shape of the orbit and the orientation of the orbit. But ultimately, those lead to where it is and where it's headed to. So that's a good answer. So all of these different values that we've discussed, the inclination, the ascending node, argument of periapsis, all of those, really, it boils down to telling you about the shape and the orientation of the orbit, and that's pretty much it. The only one that really is different is the position of the body, which is the argument or the true anomaly right here, this angle, the true anomaly. Because without the true anomaly, you know the shape of the orbit and the orientation of the plane of the orbit, but you don't know where the spacecraft is. So it's really the true anomaly that's a little bit different in terms of that rule, because it tells you in that scenario, in that orbital plane, given that orientation, where the spacecraft is in that orientation. So those are the KEPs, and we spent a little bit of time talking about them. But what it boils down to is when you want to figure out the ground truth or the ground path of your satellite, you have all of these orbital elements, right? But you might not necessarily know the mean anomaly. You might not necessarily know where the spacecraft is. You have an orbit model. But, instead of deriving the Keplerian elements from an orbital model every time you take a pass, because how many passes can there be a day of a satellite in LEO? How many passes you guys taken for Kentucky Sat 2 a day? About 4 passes a day, right? So you don't want to generate a model and derive these elements every single time, right? Because it takes a while to do that. Thank goodness for the government, because they do that for you, it turns out. So the Department of Defense, NORAD, and specifically an element of NORAD that doesn't like you to talk about who they are, so we don't, uses a system called the Space Surveillance Radar, and they track all the spacecraft in orbit around the Earth. Every single spacecraft that's big enough to be seen. And not even spacecraft, just debris. I mean, everything down from, the glove that the astronaut lost, to nuts and bolts, to, upper rocket stages, to live satellites, dead satellites, Zombie Sat. You guys hear about Zombie Sat last year? Yeah, that was a good story. So they're all tracked by Space Surveillance Radar. And so NORAD then uses the data from Space Surveillance Radar to produce what they call the Keplerian elements, or the KEPs, or the TLEs, two-line elements, for every single spacecraft, for every single piece of orbital debris, for everything that's up there that can be seen by the Space Surveillance Radar. And they post those on a daily basis, right? So you have access to the daily KEPs if you are part of the Space Network through SpaceTrack, which we have an account on. And actually anybody can apply for an account. They just have to do a background check and make sure that you're a legitimate user. Or you can get Keplerian elements that are a couple of days old, which are generally good enough, through a website called celestetrack.org. So basically you go to the internet and you pull these KEPs down, and you enter them into your operator program for your ground station, and then it figures out all the orbit model for you, and it figures out where to point your satellite when, and how to make the antenna system track the satellite across your local sky. So how then do you get from the orbital elements to the KEPs? That's kind of what I think was missing in our previous discussion. Well, here's how you do that. So each one of these sort of blocks of data in the KEPs, so 2 lines, line 1 and line 2 there, have all these fields of data. And the fields of data relate to those orbital elements, right? Unfortunately, it's not really very straightforward how you get there. And there are additional terms, like the B-star drag term, which is basically a drag parameter. And then there's some, things like a checksum that aren't part of the orbital elements. But essentially, the fields of data in the KEPs correspond to the orbital elements, and then a little bit of additional data. So here's kind of how it works out. So each of these, the very first line in both, the very first field in both lines really is the satellite ID number. So this is an example from CXBN from last year, and it was object in the International Catalog 90035U. So that first field in both lines is the catalog number for the satellite. And then there are other things like international designators, and then the epoch, the year and the date, and then you get things like the mean motion and the drag term and the checksum. But let me show you a specific example so you can see how it works out. Oops, I need to go back. Previous, there we go. So here's an example. So this was the KEPs that I pulled on a specific day last year for CXBN, and you can see the fields there, and then you can see exactly how which of those fields corresponds to which of the orbital elements. For example, again, the first line, the first field in both lines is the catalog number of the satellite. The inclination is 64 degrees. So it corresponds to, I don't think inclination actually has a decimal. I think the decimal might be understood. Do you guys see where 64 is in that string?
It's in line 2, yeah.
Line 2, yeah. The first, it actually does have the decimal. Some don't. So it's the second field in line 2 there. So that tells you the inclination. The right ascension of the ascending node. Remember the angle between the plane of the orbit and where the plane intersects the ascending node, and the argument, or the apogee, is the right ascension of the ascending node, and that one, the decimal is understood. So can you see where that one is? No, I'm sorry, that one has the, I promise one has no decimal. So it's the third line over, the third field over, I'm sorry, in line 2, right? See, 291.4359 is there. It's the eccentricity that has no decimal. So the eccentricity is 21 degrees relative to the ecliptic plane. And you can see that it's the next line over, or the next field over in line 2. 1, 2, 3, 4. So it's the fourth field over in line 2. And then the argument of perigee is in there, the mean anomaly. And then there's some additional things like the revolutions per day, basically the number of orbits in a given day, number of orbits per epoch since it started, since it was launched, and then a checksum. So you don't really have to know, to be honest, to be able to track the satellite. You don't have to know what these orbital elements are. All you got to do is go to the website and snag these elements, right, and put them in a text file. But the thing is, you have to be really careful because they're very particular about having, additional data in there, or if you got spaces in there that you don't need, it won't take it necessarily. So you'll learn how the operator program works, and when you pull these KEPs in, you'll see how particular it has to be to merge those files to give you an updated set of Keplerian elements to track your satellite. But the point here is, behind all this, is that's where these KEPs come from, is they come from the orbital elements that tell you about the shape, the orientation, and the position of the satellite. And then the software does all the magic. So all you got to do is pull these KEPs in, enter them into your program, and then your antenna is going to know where to point, when to point, how to track across the sky, and when the satellite's going to appear. We have to run the models first, though, so we create a schedule so you know when to go down there. Because even with the UHF system, you might have noticed if you've run it. How many people have run the UHF system so far? Oh, almost everybody, right? Okay. If you haven't, please get your hands on it and just do it. So we have a meeting at 5 o'clock every Monday, right? The ground ops team, we just started this Monday. Everybody's invited. Just go and show up and work with somebody one-on-one who knows how to do it, and get trained. And then we'll cut you loose and you can do it by yourself or in small groups very quickly. So, and I'll give you more information about the meeting. But anyway, that's how you relate the Keplerian elements. The TLEs is mostly how you'll see them referred to back to the common orbital elements. Okay, so and just when you go to snag them from, there is another direct NORAD place you can get them from, but you can't typically get an account on this site, which is JSPOC, the Joint Space Operations Center, operated by NORAD. But basically, they all kind of look the same. When you go to CelesteTrack or spacetrack.org, you'll have the catalog number. You'll have to enter it. Maybe you'll do a catalog search. How do you find your satellite in those catalogs to get your TLEs on those websites? You just basically enter the catalog number. Soon they'll have common names. So it probably will be another month before you can type Unisat 5 in or Kentucky Sat 2 and actually get the Keplerian elements out. But for now, we're pretty sure what catalog number is which satellite. And then basically you just hit the hot link to get the latest data set, the TLEs, and then it pulls up those two lines. And then you can take those two lines and just copy them into a text file. And that's pretty much it. So that's how you get the TLEs and where they come from. Well, then what happens to them? Just as a little bit of a reminder, the flavors of orbits that we mostly work with are LEOs, MEOs, GEOs, and HEOs. Remember what they stand for? And AEIOUOs. Tough audience. What's LEO stand for? Goes out to where? How far? How much?
2,500 kilometers?
Yeah. Okay, that's acceptable. How about MEO? I always want to say Middle Earth orbit, but it is not. Oh, come on, you guys are geeks. That was funny. Middle Earth? No? Nobody? Okay. Medium Earth orbit goes out to where? Yeah, excellent. And then GEO is at what specific distance? There you go, exactly. Are they on there? Oh, jeez. I really didn't think they were on there, actually. Damn it. Yeah.
Yeah, I knew that.
Okay. But you guys really, you had a feel for those numbers, right? Yeah, you might, Geo, you might have seen in miles or nautical miles, but you probably have a feel for those numbers. All right, Will, you smarty pants kids, what's the distance for HEO then?
It varies.
Damn. Yes, that is true. All right, moving right along. And so how does that all relate then to the ground path, the orbital trajectory? Normally, when you pull up your screen on your operator program, and we use a couple of different programs. We use, for the Yagis, we'll use, or the UHF ground stations, Yagi-based antennas, we'll use an amateur radio operator program, typically Ham Radio Deluxe. And for the big dish, we use a proprietary set of software called hardware control. But they both end up pulling up graphics like this when you engage the satellite tracking component. And so they bring up a graphical user interface, and they all have some sort of graphic that looks like this. And you can monkey with the settings, and it'll show you the orbital path of the satellite of interest. And you can display lots of satellites, or just the one that you want to look at, or whatever. And normally they'll even show you a little dot of where the satellite is, and then you can even put a footprint around to show you what the sort of the contact zone is, called the satellite footprint. But that's essentially what they look like. Can you tell what kind of orbit the satellite is just by looking at the ground trajectory? Is it in an equatorial or is it in a polar orbit, for example? Yeah, it's a polar orbit, right, exactly. So it's a high inclination, right, because the ground path goes way high over the poles. Yep. And so just to give you a feel for what they typically will look like, this is an image pulled right from your book, by the way. If I had to choose one of those that was primarily in a low inclination, i.e. a quasi-equatorial orbit, which one would it be? A. Okay, for B, can you tell me what the inclination would be for B? If you had just eyeball it. What's the latitude of Moorhead? 38 degrees, exactly. So that one doesn't quite go to Moorhead. It goes to, Houston.
So like 20?
Yeah, 20, 30, something like that. And you can tell by the maximum altitude that it reaches equals to the inclination, right? So what would you call the inclination of satellite C there? About 50, yeah, exactly. And then D goes way high. So D's pushing polar, and it's something like 85 or so. These all have the same orbital period. What if I had a longer or shorter period? What if the satellite was moving faster or slower? How would the graph change? That's exactly right. Yep, they would be more elongated if it's moving faster and has a shorter orbital period, and more scrunched together if it has a longer orbital period. Okay, so there's some good examples in the book that you can look at. Okay, what does that all really mean to you when you're sitting at the consoles getting ready to take a satellite pass? Well, here's what it means. So here you are at home in Moorhead with your dish or your Yagi waiting for the satellite to come overhead. And so on your display, you'll see the ground path of the satellite, and then you'll see some data on the satellite that'll say AOS in T-minus 2 minutes. So what do you think AOS means? That's exactly right. It's the point where you can see the satellite, where it barely peaks above the horizon, and it's acquisition of signal or acquisition of source. Okay? And so then it goes overhead to your zenith, right? If it's a high altitude pass. Sometimes they don't. They just skirt along the horizon, and you might have a low altitude pass. And then LOS then is for loss of signal. That's exactly right. So all of that will be displayed. Whatever graphic user interface you'll see AOS, you'll know when it's coming up. You'll see the maximum altitude when it passes the local meridian. You don't really want it to go over zenith, but you don't want it to be too low either, right? So let's think about that for a minute. If the satellite pass has a maximum altitude of, say, 5 degrees, what's wrong with that? Is that a good pass or a bad pass? That's a bad pass. Because you're going to be looking in the trees, you'll be looking at the hills, the trajectory above the horizon. You might only have a couple minutes to pull your data down and send up your commands. Those are anything below 10 degrees is not really a good pass, unless you're using the big dish. You can track the big dish, the satellite's down to -1 sometimes. How can you see a satellite below the horizon? I promise we've done this. I wouldn't have believed it myself, but I have done it myself. You can see it below the horizon, before AOS. You're pointing toward the horizon, and you can go a little bit below the horizon. But you're looking at the Earth, right? Well, you get some refraction of the signal through the atmosphere. So before the satellite literally physically rises above the horizon, you can get refraction of the radio wave into your dish, and you can actually track it below the horizon a little bit. Isn't that crazy? So the big dish is a little different. With the Yagis, 10 degrees. That's anything under 10 degrees is a bad pass. Don't even waste your time unless we're really trying hard, like with Unisat 5, to find your satellite now. A directly overhead pass is great. Why? But there's limitations, right? So why is it good to have a pass that comes way overhead? That's exactly right. Think about all the time you got to pull the data down, to see the beacon, to send up commands, whatever you got to send up. And so these pass times really aren't that long. I mean, there might be, for a low altitude pass, you might have a couple, 3 minutes. For a real high altitude pass, you might have 10 minutes, 11 minutes at the most, ever. Right, so all of that has to be done. So you got to be ready. You got if the user, the developer or owner, the manager of the satellite has you issue commands to it to turn instruments on or off. You got to be ready with those. Typically, what you're going to start doing is just pulling down data and telemetry from the beacon. But then, when you become, advanced users, we'll actually have you issue commands up to the satellite, which is you got to be pretty good at that, because things could go badly wrong if you issue the wrong command, because you could kill somebody's satellite, for example. There have been examples when operators have turned the high gain antenna away from the ground, and you've lost contact with the satellite for a period of hours, and occasionally that has resulted in the loss of tens of millions of dollars of revenue. If you're talking about data transfer or financial transactions. So you have to be very careful when you issue the up commands, the uplinks. There's a problem, though, with directly overhead passes, right? So the problem with the big dish is called keyhole, right? And what keyhole means is that the dish can't plunge over. So if it's looking at the horizon and the satellite's coming directly overhead 90 degrees, it can't go higher than 90 degrees altitude, right? So when the satellite's directly at zenith, when it goes past zenith, the dish can't whip around infinitely fast in azimuth. It has to whip around theoretically to cover the whole trajectory. It would either have to be able to plunge over, which is very difficult to do with big dishes. Would it cost another $1 million to make it do that? Or you need to move infinitely fast in azimuth to track it on the downhill run, and you can't do that. So there's a region called keyhole where you lose data, right? And so our keyhole's about at 77 degrees altitude for the big dish. So you just know you're going to lose data at high altitude passes for that keyhole region. The Aggies can plunge over. They'll just plunge over. So there's minimal keyhole effect with the Aggies. They don't weigh that much. It's easy to do mechanically. So the Yagi antennas, in most cases, are able to plunge over so you can track. So there's very minimal keyhole. There's Doppler effect, though. So when you're looking at the satellite, you're expecting to see it at one frequency or another. And where are you going to get the maximum shift from the expected frequency and minimum shift from the expected frequency? When it's coming toward you, it's going to be blue shift a little bit, right? When it's at zenith, there's no shift. When it's going down, it's going to be red shifted. Exactly. What if I'm looking at it on the horizon just doing this kind of thing? Basically no shift at all, right? So there's all kinds of parameters to make it a little bit challenging to actually be able to track satellites and pull down the data. So you got to understand a little bit of the physics, a little bit of orbital mechanics, so when things happen, you just sort of know what to expect. If you're tuning your radio in very precisely, you'll have to account for the Doppler, but we have this thing called software-defined radio, and you can look at honking broadbands of frequency regimes, and so you don't really have to worry too much about the Doppler. And actually, the radios will account for Doppler shifts. They'll use the trajectory models and account for Doppler shifts too. But just so you know what's going on there. Okay, so to kind of wrap up, then, when you're sitting at the console and you're ready to take a pass, here's what sort of a day in the life looks like when you're the satellite operator and you're getting ready to take a pass. So we have a schedule that's issued every Monday, and it has a schedule that you can sign up for to take certain passes. So please come to the meetings on Monday nights at 5. And if you can't come, we'll get you on the list and make sure you get access to the schedule anyway, and you can sign up. Initially, I would recommend that you sign up with somebody to go with somebody that's done it before, so they can train you a little bit. But after a couple, 3 times, heck, just sign up and try it yourself. The best way to learn is to try it yourself. And the neat thing is, we're getting so much data from these satellites. If you totally screw it up and you miss a pass, right now it's not that big a deal, to be honest. We'll just catch it on the next pass. Now, when we start taking images of the Earth, those are kind of critical. With Kentucky Sat-2, we want to get those data, that data down, and so we'll want to make sure we got experienced users there. But right now, we're just tracking the beacon and getting telemetry down. So get your hands on it, just try it. You know, if you mess it up, it's not a big deal. With the Aggies, not with the 21 meter. Okay, so here's what a typical pass looks like. So you look at your schedule and you've signed up. You knows when to be there for your pass. You get there about 10 minutes early. You got 2 computers to work with. You got the computer that VNCs into the controls for the antenna itself, that controls the antenna, and it's going to run the satellite tracking program that shows you the ground pass, and it's going to have all the information about the trajectory. And then there's another computer on another table that's basically the data acquisition computer, right? So it's pulling down the data and the telemetry. So you got to kind of man 2 computers at the same time. So it's a little bit tricky. So you get there and you configure on the computer that drives the antenna, you configure the satellite tracking program. And I have an operator's manual, by the way, I'll send around if you haven't gotten it already. And it kind of walks you through these steps. So you configure the satellite tracking program. In the case of the Aggies, it's Ham Radio Deluxe. And then you walk over and configure the back-end computer, which essentially has the receivers all set up. When we get into this at the next level, we'll worry about all the telemetry receivers, the bit syncs, the frame syncs, and all that. But this is all sort of already set for these particular missions, so you don't have to worry about that now. But you do have to configure the digitizing or data recording computer, in other words, the data analysis computer. Then you go to a website, unless somebody's already sent you the TLEs, and you import your TLEs into the program. Then you initiate the track algorithm. It's called DDE track, I think, on the Ham Radio Deluxe, and it initiates the track prior to AOS. And the antenna basically just sits there on the horizon before the satellite. It knows where to point in azimuth, and it's just sitting there on the horizon waiting for the satellite to come up, peek up above the horizon. When it peaks up above the horizon, when it starts to, you can start to hear the rotors click. They'll make a clicking sound. That's a good thing because you know the rotors are going to drive the antenna. And then the satellite picks up above the horizon, and it initiates the tracking algorithm. And then you can sit back and just watch it. We typically like to look at the altitude. And usually we have one person at the controlling computer and another person at the data acquisition computer. Sorry. And then you can look at the beacon, the data coming down in real time. That's really cool. And there are 2 ways to look at it. There's on the data acquisition computer, for all satellites, we have 2 ways to look at the data. We have proprietary software for, in the case of Kentucky Sat-2 and Eagle 1, it takes that data in and it strips the data into telemetry, and it just shows you the bits going into a program. A more generic way to do it is to look at the waterfall display on the software-defined radio, and you can see the beacon graphically on this beautiful waterfall display. And you can look at the frequency and the beacon interval, that is to say the interval between the beacons, and you know exactly what that is for a given satellite. Every satellite has a unique frequency, transmits frequency, and a unique beacon and a unique modulation mode. You can see all that on the display, so you know who satellite's who. So you can literally see the satellite data coming in real time, which is pretty cool. And then you, after you've acquired the beacon, you download the data in telemetry. Really, it's automatic. It just spits it into those proprietary programs. If you have been requested to upload a command sequence, you'll do that. And then, that'll be very specified by the manager, the program manager. And then after, 7 or 8 or 10 minutes, you have LOS, loss of signal, and you're done. So then you save your data file, you submit it to the appropriate person who requested the data, and then you park the antenna, and then you plan for the next pass. So that is a day in the life. But let me tell you how exciting it is to see the data coming from space on a satellite that you've set up. That's pretty cool. You guys can do that like today, tomorrow, over the whole break. But when you actually get the first data from a satellite that you built on orbit, that's a whole different level of just ridiculously cool. So, and you guys will have that experience. So right now, please, sign up for some passes, get your hands on the instrument, start learning the mission ops into things, and again, it'll help you train to get a job and become rich and famous satellite operators. Okay, questions?
That's a good start, all right, to look at the questions, and if you find any questions that you can't answer, you can't find them in your literature, all of the stuff that you've saved in your book. If you can't find it, let me know, and I will help you find it, okay? But the things that you need to calculate is I'm going to give you a satellite, and I'm going to give you the altitude on the satellite. So what can you calculate from the altitude? Anybody? The what? The velocity. Okay. Now you got the velocity. Can you tell me what the maximum pass time would be on that satellite? Okay. No, you can use the chart, because I'm going to give you one that's not on the chart. Aha, aha. So, it might be 413 kilometers high. So you got to be able to calculate it. So and then if it's a noon midnight, you've got to be able to calculate the maximum eclipse it's going to get. Is the eclipse important? If I give you the altitude and the things that you calculate, can you tell me what the inclination is on the orbit?
I'm going to go with yes.
Pardon?
I'll say yes.
You don't have enough data. All right? If we told you what the ground track looks like, could you calculate or could you estimate the inclination?
You know the altitude? Yeah.
You know the altitude. And I showed you a picture of the ground track. We've seen some ground tracks up there, right? Could you tell me what approximately the inclination would be, right? How?
What degree latitude, like it
How high it goes, right? That's the inclination. Cool, huh? Can you calculate Doppler?
Doppler shifts?
Huh? Doppler frequency change the needed by the radio. Do you know what Doppler is?
Yeah, I don't know how to calculate.
That comes next semester. Okay, so I'm not expecting you to do that. So, take a look at that stuff, and I'm going to give you, a few little problems to do. So be prepared to calculate something. And maybe what I'll do is I'll hand out 2 or 3 sheets of example calculations. Yeah. Yeah. Okay?
You know what day the final is?
Tuesday.
You think it's at the same time?
Same time.
Tuesday.
2 hours.
So it's Tuesday, what, roughly 12:40 to 2:40?
Oh, man.
Next, it's a week from today.
That's 2 finals back to back.
A week from today. Okay?
Pretty depressing.
We had Mike's final right before this class.
No.
Okay.
One on Friday.
All right. Okay. Any questions? Who wants an ops job? All right. All right. Okay. Because you need to study, we'll let you out early. Anybody object? Okay? All right. Now, if anybody needs electronic copies of any of the notes that are there, go to the Blackboard and go to the Dropbox site that I give you, or send me an email. All right? Cool. Thanks.